Never be afraid. There's nothing which is known which can't be understood. And there's nothing which is understood which can't be explained. For over 50 episodes now, my team and I have brought you to the very frontier of knowledge in physics and astronomy. And still, our mission goes on. To present you with your birthright, an understanding of the universe. I've traveled the world seeking out a certain type of genius. Masters of not only their academic disciplines, but also at explaining their research in understandable ways. And I've bestowed upon these women and men the title of Titanium Physicist. You're listening to the Titanium Physicist podcast, and I'm Ben Tippett. And now, allez, physique! The movie Austin Powers, International Man of Mystery, is perhaps a victim of its own success. It came out in 1997 and was a heartfelt parody of the James Bond franchise of films. And parody is so hard to do well. A super spy is frozen in the 1960s and is revived in the 1990s to fight an old enemy. The movie was a smash hit, not because of its well-written and disciplined humor, but because of the style of the thing. Austin Powers brought with him the style of the cool mod subculture and the swinging free love of the 1960s, and all the young people were like, yeah, shagadelic. Weird. Anyway, it was so successful that they made several sequels, and they weren't very good. So I mentioned before that the humor in the first movie was tight. It was very silly. Yes, it was a parody, but they didn't overlook the little details. In one of the most famous scenes, the villain, Dr. Evil, has just jumped to the late 90s and rejoined his criminal organization, and he begins spitballing plans to take over the world. Each plan he proposes is shot down by his employees. The joke being that most of the things he proposed, which by the 1960s standards seem horrible, have already happened by the late 90s. So Mike Myers playing Dr. Evil goes something like, back in the 1960s, I had a weather-changing machine that was in essence a sophisticated heat beam which we call a laser. Using these lasers, we punch a hole through the protective layer around the Earth, which we scientists call the ozone layer. And of course his employees shoot him down because in the 1980s we had to ban CFCs because they'd already eaten a big hole in the ozone layer. But the thing that makes this scene great is how Dr. Evil explains these things to his employees. He knows they're not scientists, and so he introduces the technical words by saying them slowly with air quotes. The word ozone is the name of a chemical, a rather rare type of oxygen molecule. And the word laser is a technical acronym. And lasers were not common technology in the 1960s. They are now, though, and that's the joke. But noticing that lasers would seem anachronistic to time travelers is characteristic of the type of detail which made this parody so tight. Anyway, lasers, right? Laser, it's an acronym. Light amplification by stimulated emission of radiation. It's a machine that shoots a really bright dot of light. And unlike, say, a flashlight where the light gets weaker the farther you are from it, the laser's dot doesn't seem to get wider or weaker the farther you get from it. It stays just as bright. So, how do these laser things work anyway? Today, on the Titanium Physicist podcast, we're talking about lasers. Okay, my guest today is a software engineer and a clever and accomplished gentleman. Mr. Aaron Fischer lives in Seattle and has worked for companies such as Intel, Amazon, and Microsoft. He currently works at Redfin, the real estate brokerage and technology company. Welcome to the show, Aaron Fischer.
Thanks for having me, Ben.
All right, I'm so excited. So, Aaron, for you today, I've assembled a fantastic combination of titanium physicists. It turned out that these two titanium physicists know each other, unbeknownst to me, back in the day when I first had them on the show. So I said, yes, let's combine them. Let's make a super pair. Just for you, Aaron Fischer, arise, Dr. Abby Shockley.
Boop, boop.
Dr. Abby did her PhD at the University of California, Davis. She's now at the University of Paris, South 11, working Laboratoire de Physique des Solides as a postdoc studying nuclear magnetic resonance. And arise, Dr. Tia Miceli.
Boing, boing, boing.
Dr. Tia did her PhD at UC Davis, and she's currently a postdoc for New Mexico State University, posted at Fermilab, where she's an expert at nuclear particle physics. All right, everybody, let's start talking about lasers.
So the first thing that we need to understand how lasers work is we need to understand how the energy levels in an atom work. I'm sure you remember what an atom is from like high school chemistry, right? You have a positive nucleus with all of these electrons flying around in clouds outside. So each of those electrons, they're layered from the inside out and they have different energies. So the different energies that the electrons have in the atom, they're quantized. So there's a fixed pattern of orbits that electrons can make around the nucleus of the atom. And it's a fixed pattern because of quantum physics.
Everything is discrete, right? So like it jumps up a level. That means it's farther out in the orbit?
Yeah, exactly. Yeah. So the electrons can switch between these different shapes of orbits by having different energies.
Yeah.
And so these electrons are only allowed to have discrete energy levels, and based on each one, you'll get a different orbital shape. And so we need to understand that when you excite one of these electrons and it goes into one of the higher energy states, when it falls back down to its home state, we will know exactly how much energy is released. And that energy will be released as a quantum of light. It's called a photon.
Is the reverse of this the Einstein photoelectric effect? Like you shine a light on something and electrons pop off? Can I think of it as the opposite of that?
Yeah,
okay.
Exactly. So in Einstein's photoelectric effect, you shine a certain wavelength of light onto a metal, and then it will have enough energy to kick out one of the electrons from a specific energy shell, and it becomes a free electron. So in what we're about to talk about in lasers, we have an excited electron, and it will relax into its base state, and it will give off a very specific frequency of light. It gives off a photon. So we know that light has both a wave-like property and a particle-like property. It's something called duality.
So this wave-particle duality of light thing, light can be described as two different things. So like a wave, like what you see at the beach, you see waves or standing waves that you can get that from like a slinky. If you hold it between two people and start shaking it, you can get standing waves. So light is like that, but light is also, instead of like a wave, which is a big composite object, is one unique thing that's entirely to itself, though it's a particle as well.
So the duality thing I have tried to wrap my head around a lot, and I kind of gave up. The whole thing, like we have an atom and we have electrons, and they get a little excited, jump up a level, and then they can't hold it, so they drop back down but kick out a photon, and that photon comes out. Like, for the purpose of where we're going with lasers, like, should I put on my wave sunglasses and just think of it as a wave, or is it more useful to focus on its particle properties?
It's both, actually.
Yeah, that's the tricky thing about light, is that you have to wear both sunglasses at the same time.
The deal is that we knew that light worked as a wave a long time ago. 1800s we figured it out.
The particle thing, though, was fairly new.
That's right.
This idea that it can be both.
Yeah, so we figured out that light works like a particle with Einstein's thing you mentioned.
Einstein photoelectric effect.
Yeah, the deal with that is you take two different colors of light. One of them is really intense, but kind of reddish. The other is really, really blue, okay? Mm-hmm. And you tune them so that they have the same energy output, Okay? One of them has the energy output in terms of being really blue. The other achieves the same amount of energy by being red, but really intense. And if you shine them both on a metal, what'll happen is the one under the blue light, the metal will start spitting off electrons. The one under the red light will not. And when you think about this, it doesn't quite make sense because they're both putting the same amount of energy into the metal. So why is it that the ones that are blue make the electrons jump off and the ones that are red don't make the electrons jump off at all? It's because, essentially, in light, the energy must be carried in terms of little, we imagine them as little balls, little particles.
Packets.
And the energy of each of these packets is determined by what color the light is. So the bluer it is, the more energy it has. And so, from the perspective of one of these electrons that's circling and circling the atom, when it gets hit by a little bit of light, it gets hit by, one red photon and then another red photon, and each time it gets hit with one of these photons, it looks at it and says, this isn't enough energy to escape. And just because there's lots of them doesn't mean that it can use any of them. It's kind of like when you go to a parking meter that only takes quarters and all you have is nickels in your pocket, right? And you're like, I'm pumping nickels into this thing and it's not giving me any money, right?
So exact change is required.
Yeah, exact change or higher is required. And so the blue photon comes in and the electron says, this is enough to escape. And it will take that and it will turn it into energy and it will hop off the atom.
So the required energy, is that dependent on the particular type of atom or the electron orbit level? Or is it, would the red light work in one atom but not another?
Yeah, so technically I think that it will, but it's usually put in terms of a lower threshold. Any light that's higher frequency than a certain threshold will give the electrons more than enough energy to escape.
Okay.
Now, what T was mentioning before is the transition between orbitals, which is to say, right now we've been talking about electrons that are getting enough energy to escape completely, but around each atom, based on quantum mechanics, there are different orbitals that one electron can jump between. And going from a near orbital to a distant orbital requires a certain amount of energy, which it takes in and then gives off. And those are really, really specific frequencies. Okay? So to transition from the first orbital to the third orbital can only be done with a very specific frequency of photon. And so if it has that, it can jump between them. And if it jumps from the third orbital down to the first orbital, it will emit a very specific frequency.
Okay, this might be my software side kicking in, but can all of this be reduced down to like some multiple integer of the Planck value? Yeah. Is that the right thing?
Yeah.
Okay. And the higher the orbital, roughly, the higher the multiple.
Yeah.
Yeah.
So this is essentially what other physicists discovered at the turn of the century. They were doing spectroscopy on gases. So they were taking the light emitted by a hot gas, like the sun, and they were taking a prism and using this prism to split up the light emitted. And they saw that, well, if you shone white light through a gas, then the white light... Yeah.
Is this some Canadian thing?
What?
It sounds funny to me.
If you shined?
If you shone.
Shone? Wow. Regional dialects.
Sean is a name.
Yeah.
That's great. Okay, I'm going to stick with Sean because that's my regional dialect.
Oh my god, that's going to be really confusing.
It really is. Okay, go ahead.
If you take some white light and you shine it through a type of gas that only has one type of atom in it, the white light that passes through, if you take that white light and you split it up using a prism, you'll see that it's missing some key frequencies. It'll look like the normal rainbow, but a little bit of red is missing, a little bit of blue is missing, a little bit of green is missing. And those correspond to the atoms that the light is passing by, grabbing, as it passes by, the photons that allow the electrons to transition between states. And so this photon, it'll say, well, there's a whole bunch of different photons passing through. That one there is exactly the one I need to jump from the first orbital to the third orbital. It'll grab it, jump up to the third orbital, and then the resulting spectrum will be missing those frequencies.
Okay, that slightly confuses me because previously we talked about the level jump happening. We didn't give it a time bound, but kind of momentarily, like it wouldn't hold on to it. Can you shine enough light on an atom that it jumps up an electron orbital level, but stays there? Like, can it keep it? Or does it always have to emit it and relax and go back down?
I think it always emits it.
So if that's true, then how come in the spectroscopy signatures you're describing, wouldn't it just absorb the one particular matching frequency of the photon and then emit it right back out, and so you'd still see the full rainbow? Like, it's absorbing it and keeping it, right? Or sending it off in a different direction?
I think it will re-emit it randomly, which means that they're not re-emitting them all at once. There's some kind of time frame over which half of them re-emit them.
Okay.
So if you take this light and you shine it on it and heat up the atoms and then turn off your backlight, the atoms will then release these photons. And if you take the light emitted by this and hook it up to a prism, what you see is, instead of a spectrum of lights, you'll see these individual lines corresponding to the atoms re-emitting the photons.
I think I understand. Like, if the light source is steady, as it is in the case of a star, then the atom is grabbing the photons with the matching compatible frequency, shall we say, and it's not necessarily holding on to it, but it's temporarily holding on to it enough to disrupt the propagation of the light that us as the viewer see a missing band.
That's right.
Okay.
It's true that if you have a gas and you heat it up enough, eventually the holes will fill in if it's in thermal equilibrium, and you get something called black body radiation, which is a continuous spectrum. But if you have some light that's not the same temperature and you shine some light through it, it will absorb these things. Okay, so we're cool.
Yeah.
Now, there is a quantum mechanical effect called stimulated emission. I mentioned earlier that usually what happens is the electron at the third orbital will decide to go down to the second or the first randomly. It's like it has a coin that it flips, and then as soon as the coin flips up heads, it goes, all right, I'm going down to the first one. Here you go, throws out the photon, wanders back to the first orbital. So usually that's a random thing. It's flipping the coin. What you can do, though, is if you have one of these atoms where it's been excited, so the electron's up at the third orbital, and you send a photon that has the same frequency as the photon the electron would want to emit if it went back down to the first orbital. Let's suppose it emits a light blue photon, okay, going from the third to the first. And then if a photon comes by and that photon has the same frequency, it's the same light blue as the photon it would emit going from the third to the first, then that photon passing through will stimulate the emission. The photon will say, hey, I'm passing by, why don't you throw up that little photon you're holding, and then we can go together. And the electron goes, all right, I'll throw these two photons together. It picks up the photon it's holding, it throws at it, they go off and away, and it goes down to the first. Okay?
Okay, so it's a cascading effect?
Kind of. It's referred to as stimulating emission. The deal is that on a larger scale, if you have a whole bunch of gas, and all that gas, they're all excited, if you emit one photon over here on the right-hand side and it comes in and it's just the right light blue, it'll hit the first atom, cause the first atom to release its own photon, and then there'll be two photons, and they'll come out, and those will hit two others, those will release four, and that's the cascading effect that you can get. And that cascading effect, it's the phenomena at the heart of what we use to make a laser.
But if you didn't have the initial blue photon entering the system, all the atoms already stimulated in the system would randomly discharge their blue photon anyway, eventually, right?
Yeah. One would randomly emit a photon, and then that photon might cause its own cascade. Yeah.
Okay.
So stimulated emission is really weird because it's a completely quantum mechanical phenomena. The reason it happens has to do with us describing how the electromagnetic wave interacts with an excited atom.
Aaron, you knew that light was also an electromagnetic wave, right? I don't think we talked about that.
Going back to duality, the photon is an excitation of the electromagnetic field, right? That's one way to think about it.
Yeah. So, at the heart of lasing, that's the verb given to this process. It's called lasing after the word laser. It's stimulated emission of light. What you can do is you can have this ball of gas or something, and in one direction, you can excite it, right? So how do the electrons get up to the third level? Something comes by and gives it enough energy. It can be a whole bunch of different things. It can be light, where, as we mentioned before, it steals some of the photons passing by to jump from the first to the third level or whatever. You can stimulate it by hitting it with something. You can send in an electric current And all those moving electrons shove the atoms, and in the process of shoving the atoms as they pass by, the electrons inside the atoms jump to a higher level. There's a variety of ways to do this. And this procedure in a laser, we refer to it as pumping. And what we do is, if you keep on pumping a material, if you keep making sure that most of the atoms in this system are at the higher energy level, you can get a really effective way to get this cascade of one light blue photon knocks off another light blue photon, and by the end you get a whole bunch of light blue photons moving out. And usually that cascade would deplete the system and bring everything down to the lower energy level. But if you're constantly adding more energy to it, the system will kind of stay in the higher energy level, and you can keep cascading the system.
Okay, you're keeping it full, basically.
Yeah.
And is it accurate to think of this as just the cells in a battery constantly being discharged? Like, I'm charging my cell phone, it's still operating, so it's discharging and charging at the same time, but it has a steady state, like fully charged battery. Is that not a bad analogy?
Yeah.
Like, I'm just picturing a bunch of atoms sitting there, and each one of them is flipping the coin, like you said.
Yeah.
Does it matter how much total energy you're pumping into the system, or does it just have to match the frequency of the blue photon in this case? Like you can't control the randomness of how frequently it's pumping out, can you?
So you're asking, can we control, how bright our laser is? And we do that by having a more intense or less intense source for pumping.
That's the heart of my question, and this is a good software way of thinking about this. Like, if I have a laser that's being driven by just one atom, going back to what you said earlier, everything's quantized, right? So everything's discrete.
Right.
And I'm picturing just a single file stream of blue photons at whatever frequency coming in. And there's only going to be so much absorption and discharge of the resulting light, regardless of how many blue photons I'm bathing into the laser. So I guess, is the only way to scale this thing up with just more atoms? Or I guess the intensity part of the laser I don't quite understand.
There's two parts to the intensity of the laser. There's this one that you have a whole bunch of photons, okay?
Yeah.
That causes it to be more intense. But there's something else. So up until now, our description requires only the particle nature of light. We can describe everything in terms of photons, right?
Yeah.
So essentially, your stimulated emission is just like you have a whole bunch of houses on a street, and each house has a little kid, and they don't know when to go to school. And then one kid at the back of the row goes, "I'm going to school." And then as he marches down the street, all the other little kids join him. And they're like, "Yeah, let's go to school, hooray." And then you end up with a whole bunch of kids moving down, a cascading number of children. Fine.
Okay.
That's still all quantum. That's still all particle nature. The reason we need wave nature has to do with a phenomena called coherence. It's entirely seen from the wave point of view of light. I'm sure that you've seen a diagram of what an electromagnetic wave looks like, right? It looks like a sine wave.
Like two sine waves, really.
Like two sine waves?
Yeah, because there's the parallel and the perpendicular part, right?
The electric field induces the magnetic.
Yeah.
Right.
Seesaws.
Okay, so it looks like two sine waves, but essentially, if you look at the electric component of that from the side, it looks like a sine wave. Nice and smooth up and down. That's not really how the light we perceive, say, coming from the sun or coming from a candle or a light bulb looks. If we were to pause time and take our little pencil and trace what the electric field looked like, it would actually look like a whole bunch of squigglies. There would be no coherent up and down to it. And part of the reason for that has to do... It's kind of like the waves on a beach, right? I mean, you think about a wave in water and you're like, well, it's up and down and up and down. But if you're in a boat, the boat goes up and down based on what waves are passing under it. And it goes blah, 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 right? There's no pattern to it. And the reason for this has to do with wave interference. The idea is that, okay, each individual photon might be up and down and up and down, but all these photons are coming at you in kind of a really disorganized way. And so their waves are interfering with each other and kind of canceling out the pattern.
Okay.
And the result is that if you analyze this thing in terms of classical waves, you see that the energy isn't being distributed through space in a very efficient way because the signal isn't very coherent. So the thing about stimulated emission of light, so back to our little atom, our light blue photon comes through, and then the electron inside the atom releases its own light blue photon. those two photons are going to march in step. They're going to align up perfectly. Their waves will be coherent. They'll line up with each other.
Sorry, I can understand how they're the same frequency, but I'm picturing like a three-dimensional, the space around the atom. Like, what guarantees that they're flying off in the same direction?
Yeah, they're essentially going to stack. This is how stimulated emission works. They end up going in the same direction, they have the same frequency, and they'll also have the same phase. They're moving. And so essentially, if you look at it from the wave point of view, your first photon comes in, and the result, the two photons, it's just like the blue wave is twice as high as it was coming in. So it leaves amplified. It's more than there are just two photons. Now there are two photons that are definitely not canceling out.
I think that's more of a practical question about how do we actually design a laser versus how do they actually work on like a fundamental level. Because I think that might make more sense when we start talking about how you make one, which is not what we're talking about right now.
Okay, sorry if I'm rat-holing. It's nothing fundamental about the way the photon's being emitted from the atom, like in the right direction. It's being emitted and being collected and stacked, and that allows for coherence. Okay, so we're stacking the light. Then what?
I mentioned before, you have a whole bunch of kids leaving their homes. Essentially, it's 7:30 a.m. It's time for all the kids to go to school. Nobody's sure who's the first kid to leave the house as they walk to school. This is an outdated metaphor. Kids don't walk to school anymore. All right, whatever. You got a whole bunch of little kids. They're ready to go to school. They see one kid walking down the sidewalk. Instead of all the kids running out of the house and just running everywhere, they're going to march together really tightly. Whoa. And so you end up with a really dense packet of children moving down the street all in one direction.
Okay, so we've converted the kids into marching band.
Oh, really? Because I don't know what's wrong with me, because I was thinking about Nazis, and I was like, this is a terrible analogy.
Yeah, that was coming to mind, too. I was like, oh, no, he's talking about like the SS kids now.
What?
Yeah.
Buying to Hitler.
They're just kids having fun. They just learned that the fastest way to run at school, if you're not going to trip over each other, because they really want to go to school to learn physics. So the fastest way they can get to school is if they coordinate their efforts and march in time.
I don't know what kind of kids that you know, but I feel like not a lot of them are like, woohoo, let's go to school today to do physics.
Well, it's because they don't teach physics until they're in grade 12. That's the reason kids don't want to go to school.
I agree.
I mean, kids don't want to wait for half a week for their birthday to arrive, right? How can they wait 10 years before they can learn some dang physics?
Without the physics, they don't know how to march efficiently, so it's a bootstrapping problem.
All right, so this is the basic things that a laser brings to the party. You end up with not just light emitted from the system, but coherent light. It's all moving in the same direction. All the light is stacking. And so you can end up with a very bright beam that doesn't kind of interfere its way out of a nice, bright, tight beam.
Sorry, in the wave view, it just has a higher amplitude? That's the way to think about this? Okay.
Sure.
Okay.
All right, Abby, tell us how to build one of these things.
Okay, I guess I'm going to start with a little bit of trivia that has nothing to do with building a laser. The guy who came up with how we make a laser died this year, like a few months ago, at the beginning of the year, which is really sad, and he's now my new hero. Like, he's quoted as saying, you know, I helped invent the maser, and then that was enough for me, and I let people go on their way, and I just wanted to go do something else, because once you know everything about something, you don't need to do it anymore. Like, that's so cool. But so this is sort of what you were getting at before, is how do we get it as a focused beam, really? So you have what's basically an optical cavity. So it's kind of the same thing that you would think of if you're thinking about how a flute works to make music. So you have a cavity, and then there are different types of things that you can put in the cavity to be a medium. So, like, the medium that we're used to sound traveling through is air, but it can take all sorts of different things. So it can take gases or liquids or solids, and lasers are made out of all of those things. But it's basically just a medium for the light to transport through. So you have an optical resonant cavity. On either side of it, you have mirrors that are just reflecting this light back and forth until it gets to the correct level to send out its laser light that you're used to seeing if you've ever played with a laser pointer.
I have a lot of questions. I don't want to flood you, but this is why I really love talking about this topic, because my career started at an internship at the Lawrence Livermore National Lab, and I was there for the dedication ceremony for the target chamber of their national ignition facility. This thing had 192 holes on a 3-story sphere, and it was 192 lasers kind of converging on one point, and I just marveled at how that could possibly work. And so one of my questions is, the power level they got this thing up to was like in the terawatt range. And so how can you have a laser that, you said it has mirrors and like the photons are reflecting back and forth until I guess they are allowed to move on to a target. Like, how do you not melt the mirrors? How do you...
So you already answered part of your own question, because they had so many different lasers pointing to the same location. So all of that energy that they were focusing down to one point was spread out through many optical cavities.
I think the stuff that's bouncing back and forth within the cavity itself isn't actually the full power that's coming out. So it's once it reaches that full power, it pops out, but then there's still light that's still trapped inside the cavity. So anything that gets to the amount of power that you're seeing in the final laser product comes out through like the hole that the light is transmitted through.
Okay. So I guess the thing I was going to ask, and it might be total silliness, is like, let's build a laser from just one atom and understand the limits of that. It's like, is there an upper bound to how strong a laser can be? Because I'm picturing like the lasers coming in, they're photons, so they can occupy the same point in space, right? They're both
bosons.
So they're coming in and they're all on the same amplitude, same frequency, and like, can you just infinitely pack more photons in the same space like that? Like, is it just... That's...
Yeah, so if you want to make a laser that does a whole bunch of intense light for a short period of time, you can open the floodgates. Before, Abby was talking about how we build it with like an optical cavity, right?
Optical cavity, yeah.
And so you put your lasing medium in, and light inside this optical cavity, light photons are bouncing back and forth inside this optical cavity, and each time it bounces back and forth, it passes through the lasing material. And every time it does that, some new photons join it. And so it goes from being 1 photon back and forth to 5 photons bouncing back and forth to 35 photons back and forth to 10 billion photons, however many, right? I'm not sure if there is an upper limit to the number of photons you can put in there, but it's probably very, very high. And so if you want to make a laser that shoots an incredible burst of energy, power all at once, you can just drop one of those mirrors, and it will let everything out. But instead what they do is they put a little hole in one of the mirrors, effectively, so that some of the photons are coming out. And so what you can get is a big herd of photons is bouncing back and forth inside this cavity, but then a steady stream of those is passing out through the hole. To make it so that that steady stream is more intense, you just need a cavity with more and more lasing material in it. That said, is there any limit to the energy you can make with a laser? It's a good question, because it's like we said before when we were talking about Einstein's photoelectric effect, where light comes in and causes an electron to get spit off some material. The deal is that the power contained in a wave of light can be dependent on how many photons there are, but also what frequency of photons there are. So you can probably make a thing that scales and packs a whole bunch of blue photons into one phase, or red photons. You're going to have a lot of trouble making photons that have really, really small wavelength, like X-rays. There are technical limitations to being able to build things like that.
And I think that was the hardest part when they first started making it. So, like, it's really easy to get the frequencies on the lower side. So the infrared and the red light were the first lasers that we managed to make. But it was much harder to get towards something that was on the blue side of the spectrum, or like violet or ultraviolet, which they can make now. I don't even know that we're at the limits of what you can do with laser technology right now.
We should talk about applications now, because one of the applications was an X-ray death laser, right, Ben?
We were talking about that.
Okay, so the deal is the American military wanted to build an X-ray laser so that it could do things like melt incoming nuclear missiles. Right? Ronald Reagan was famous for forwarding a project where they were going to put nuclear weapons in space to shoot down other incoming Russian ballistic missiles. Do you remember this? It was famously nicknamed the Star Wars Project. When I first mentioned this general topic to Tia, I was like, oh yeah, we can talk about Star Wars. And she's like, what does Star Wars have to do with lasers? I'm like, no, not those Star Wars. Ronald Reagan Star Wars. It was called Project Excalibur was the proper name of the thing. So the deal is the frequency of the laser kind of depends on this stimulated emission. You need a transition that goes from one level to another level inside of an atom and releases the right frequency of light. But you also need to be able to pump the system, right? Pumping was an important part of the system where we're constantly adding more energy to it, raising the general population up to the energy level, right? Yeah. And the deal is, if you want to make an X-ray, you need an incredible amount of power to pump the system. Way more power than what we usually use. We usually use current or flashing lights of different sorts. To do this, you would need essentially the same energy levels as you can get in, say, an atomic bomb. And so they did this, essentially. They designed the thing. The deal is, you take essentially a tube, and inside this tube you put your lasing medium. So all the stuff that's going to stimulate the emission. But we need to pump that system before we can get X-rays bouncing back and forth, right? So they wrapped that tube in fissile uranium and then built an atom bomb around it. And so as the uranium goes critical, it releases neutrons into it, bombards a ton of neutrons into the lasing medium, gets it energy enough that you can lase X-rays. And so they were going to put one of these into space, and the idea was it was going to shoot down any weapons when Ronald Reagan started the nuclear war with the Soviet Union. Luckily, they weren't able to do it good enough to do anything with it, so the project failed for engineering reasons rather than aesthetic or humanitarian reasons.
The scientists could have just been sabotaging the project because they were like, this is a terrible idea.
Oh, it's a horrible idea.
So on the opposite end of the spectrum, we have lasers, visible light, and we have masers, which is microwave. Can we do a radio-based laser? Is that useful? I'm just curious to know what all the combinations are.
So I wasn't aware of any radio frequency lasers, but I just did a quick Google search, and apparently you can use radio lasers for skin tightening and fat removal.
That doesn't make me skeptical at all. Sign me up today.
Oh, look, there's a YouTube video also.
Exciting. You know, the different levels of frequency of light that you have are useful for different types of applications. So, like, we have the Blu-ray players, so that's a blue laser. It used to be that we only had red lasers, and red lasers couldn't do as many things as the Blu-ray blue lasers do.
Huh.
You know why it is that Blu-ray discs can hold more information, right?
Can I make a guess? Is it the wavelength of blue light is smaller than the wavelength of red light?
Yeah, so essentially your optical disc drive is a whole bunch of little, they're like indentations in like the reflective material. And so when you shine the laser light and spin the disc, reflected patterns will change depending on what pattern you've punched into it. And the deal is there's a limitation on how closely together you can put these indentations based on what the wavelength of the light is. So you can't put them any closer than the wavelength of the light. And the deal is that if you want to put them much, much closer, you have to upgrade to a higher frequency, lower wavelength type light, and then you can put denser information on it, which is why Blu-ray players have these fancy blue lasers.
Huh. Okay. Oh, okay, another random question from my field. So the optical backbone that makes up the internet, and also the idea of optical computing in the future. Like Does that make use of lasers and coherent light?
Yeah.
Awesome.
The field is called photonics, and the idea is instead of having electrons send the signals back and forth, electrical currents, we're going to use light. For two reasons. One, light travels much faster than electrons. And the second reason is that when an electric current passes through things, it heats them up. when light passes through things, it just passes through things. It doesn't necessarily heat up the medium. And so you can have a lot more efficient computing that doesn't heat up so much, that also happens faster. At the really large scales, communication systems are often built using photonic relays. I'm not sure how far they have come in building photonic computers.
Okay.
Yeah.
Very cool just to know that they're all related.
I was going to say, like, on the quantum computing side, I've listened to a bunch of talks on quantum computing. A lot of people are working on in the basic research side is, like, microwave cavities and trying to get a quantum computer using microwaves. So
That would be a pretty large computer.
I know. I think they'd be huge. I think they'd be like the old supercomputers back in the day when they first made supercomputers and they took up an entire room. I think they're like that size.
Very cool.
There's a tool that nuclear physicists use to study atoms. And to study these atoms, nuclear physicists want to try to get them to be as stationary as possible. And, usually atoms are bouncing around everywhere, wiggling. Yeah. So these physicists, they use something called laser cooling to slow them down. The way laser cooling works is if you have an atom and you shine a coherent laser on it, if the atom's not moving, it will see one frequency of the laser. Let's say it's green light. But if there's some atoms that are moving away from the light, you'll get this Doppler shift. So the light will shift toward the red. The wavelength will elongate a little bit. And like we said, if you shift to a longer wavelength, that light has lower energy. So that also won't excite any of the electrons in the atom. However, if the atom is moving toward your laser light source, then it effectively sees a Doppler shortening of the wavelength. So that atom will think that the light coming to it is a much higher frequency. It will be blue shifted. And this higher frequency of light has the possibility of, exciting an electron. And then when it gets re-emitted, it'll emit it out in any direction. And so after many iterations of absorbing and re-emitting photons, you can effectively slow down an atom in one direction. So in order to slow down the atom in all directions, you need lasers pointing from all different directions onto your sample. So then you can slow it down to be able to do your studies.
So I think I remember reading some article. They said they created the lowest temperatures ever in the universe by doing precisely this. Mm-hmm. You're starting with a frequency of light that's outside the natural absorption window for the atom in question at rest. And so when the atoms eventually do settle down, the light is just like passing over them with no interaction. Is that the end state? So motion is related to temperature, right? So once it achieves this end state and the photon's passing over, it's not heating it up in any way and thus increasing the temperature. It just passes through harmlessly.
Yeah, that's right. Because those wavelengths of light, they can't excite anything in that atom. The atom is completely blind to it.
That's really cool.
The chemistry Nobel Prize and the physics Nobel Prize this year were both about light, and they were both about lasers.
Nice.
And also, this is the International Year of Light,
which is apparently a big deal in Paris, Abby.
Yeah, well, in my building, everybody's always really excited about these international years of insert science topic here.
Yeah.
So last year was the International Year of Crystals, and this year is the International Year of Light. And so they were having celebrations in the City of Light because it's Paris, and they like to talk about that, I guess.
Well, I have one last question on the applications side.
Yep.
And this really might just be a yes or no answer. But so in astronomy, they will shine like a really bright laser up into the sky to help them like normalize the light that they're seeing. Is that? Do you know what I'm referring to? I'm not...
Yeah. I think they use it in part to tune their adaptive optic systems. The deal is that there's a lot of astronomy going on, and it's fantastic, but sometimes it needs to compensate for the fact that the atmosphere gets in the way. And so sometimes a really helpful way to gauge how much moisture there is in the atmosphere and how much you need to compensate for it, you shine a bright laser straight up and then measure how much gets reflected back, and that might be an indication of how much moisture there is, and that tells you how to tune the mirrors.
That sounds like a really cool application of lasers.
Can I list my favorite application for lasers?
Yeah, go ahead.
Okay, sharks with freaking lasers strapped onto their head.
Okay, what kind of fruit do you guys want?
Mango.
Oh.
Tia, you want a mango? Okay, hold on. Where's my thing? Here it is. No, that's not it. Oh, jeez. Buttons. Nope. There. And Tia gets a mango. Mango. Abby, what do you want?
A kiwi?
All right.
Maybe Aaron wants some fruit too.
Guess.
Oh, I thought that's not the rule.
The guests get to eat the fruit of knowledge.
Yeah,
And the physicists get to eat the fruit that I give them. It's like a lasing system here. I'm feeding you. I'm pumping you guys with fruit, and you're outputting the fruit of knowledge.
Wow.
So maybe you should give us the fruit at the beginning of the show instead of at the end.
You've only just now depleted your reserves of fruits of knowledge, which is why I'm giving you fruits at the end. Well, that was wonderful. Thank you, Tia. Thank you, Abby. You've pleased me. Your efforts have borne fruit, and that fruit is sweet. Here is some fruit. Tia gets a mango.
Nom, 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 nom.
And Abby, you get a kiwi fruit.
Yum, 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 yum.
I'd like to thank my guest, Aaron Fischer. Thanks, Aaron. I hope you had fun.
I had a blast. Thank you, Ben.
All right, fantastic. All right, so it's announcement time. First, I hope you're enjoying the Question Barn episodes. They're lots of fun to make. I make them whenever I can. And so, if you'd like us to answer your questions, please send your questies to TIEfighter@titaniumphysics.com. That's TIPHYTER at titaniumphysics.com. Second, good news, everybody. Our Patreon campaign is going really, really well. We're building up all of the funds needed to start transcribing the shows. The transcriptions are being made as we speak, and every time we record an episode, we put enough money away to transcribe 1 or 2 episodes. It's wonderful. If you've got any suggestions for things we can do once we've transcribed all the episodes, including making an app or building a database or whatever, maybe a wiki, send your suggestions my way. On that note, I'd like to remind you that we are now accepting donations. We'd be grateful to receive your support, and you can make a one-time donation using our PayPal through the website, or you can set up automatic donations each time I finish a proper Titanium Physicist episode, just like the one you've heard, through the Patreon website. This particular episode of the Titanium Physicist has been sponsored by a collection of generous people. I'd like to thank the generosity of a man named Guy D., a lady named Elizabeth H., and Tony and Sam Bogue. I would also like to thank a Mr. John Keyes, a Mr. Victor C., Ryan Kloss, Peter Klipsham, Mr. Robert Halpin, Elizabeth Teresa, and Paul Carr, a Mr. Ryan Newell, Mr. Adam K., Thomas Shire, and Mr. Jacob S. There's a good gentleman named Brent Evans, a lady named Jill, a gentleman named Greg, thanks Josh and Steve, Mr. James Clausen, Mr. Devin North, a gentleman named Scott, Ed Lowlington, Kelly Wienersmith, Jocelyn Reed, a Mr. S. Hatcher, Mr. Rob Abrazado, and Mr. Robert Stietka. Thanks also to Brent Knopf for remastering our intro. I appreciate the help. Now, that's it for Titanium Physicists this time around. Remember that if you like listening to shows made by scientists where they talk about science in their own words, there are lots of other shows you can listen to on the Bracula Media Network. So go to the Bracula Media Network page and you can see all those lists. Or you can click the button. We have a special section in iTunes in the podcast store. So, The intro song to our show today is by Ted Leo and the Pharmacists, and the end song is John Vanderslice. Good day, my friends, and until next time, remember to keep science in your hearts.
Angela, don't be mad. There's something I gotta tell you, dear, before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet. Jumped through a window out into the haze. Hop down Magnolia Boulevard. No way he'll survive.
So what makes the difference between an object surrounded by lasers, like the National Ignition Facility example I cited, imparting heat, versus the same object surrounded by lasers that actually just don't impart heat but reduce the motion? Is it just frequency?
It's based on what frequency. So you have to tune up the atom that you're studying and choose the right frequency for your laser light based on what you want to study about the atom.
So there's no way you could use laser cooling to arrest the motion of anything that's not like a pure, like you can't do molecules or something.
Oh yeah, molecules have really complicated electronic structures.
Yeah.
Okay. What's that Bose-Einstein condensate? Is that created from laser cooling?
Yeah, so that's basically what the cold atom research is about.
Okay.
So, like, you have two different types of states that your things can be in. So you can either have a fermion or a boson. So a fermion is like an electron where, like, if I have one electron that's like an up electron, another electron can't be in the same place as that first electron, so that's a fermion. And then you have like levels of states that you can fill because you can't have more than two electrons in the same place because they don't like that. But a boson doesn't have that same restriction. So a boson, like a Bose-Einstein condensate, says that instead of having, so the thing I was talking about with the electrons is the Pauli exclusion principle, where you can't have more than two in one state. A boson, you can have as many as you want in a Bose-Einstein condensate. You can have as many things as you want, all on that same bottom level. You're not restricted to just two. Yeah, and I mean, that's the main difference, I guess.
Okay, like before when I was asking how many photons can you pack in the same space.
Yeah, photons are bosons.
Yeah. Bosons.
So they work. I'm not sure if you'd call the light coming out of a laser the coherent light is a Bose-Einstein condensate, but they are bosons. We are taking advantage of the boson nature of light doing that.
Last question on this: the Bose-Einstein condensate as a type of matter or class of matter, is that only achievable with laser cooling? Like, it doesn't happen naturally anywhere else in the known universe?
It does. So there are some other things that form Bose-Einstein condensates, like a superconductor in its like lowest state is sort of that same type of thing. Like, it's a very special and very unique class of things that can happen that not a lot of materials can make. So this is laser cooling with the Bose-Einstein condensate. That's a very special, unique case, I would say.
A long time ago, we did a show on
liquid helium does that too.
Yeah.
I forgot it.
Yeah, it's a superfluid. Superfluid helium is a Bose-Einstein condensate.
Superfluid helium kills me every day.
Every day it kills you? You should be more safety conscious.
Okay. Very, very awesome.